Vanakkam. Welcome to this course on biomedical instrumentation. We have been discussing about various types of sensors. In the previous classes, in the previous videos, we looked at resistive sensors, we looked at strain gauges, we looked at thermistors. In this video, we will start our discussion on capacitive sensors. From our high school physics, we know what a capacitor is. Usually, and for these applications, we are looking at a parallel plate capacitor. That is, there are two plates that are separated by a dielectric or an insulator. Now, what is the capacitance of a parallel plate capacitor? We know this from high school physics, and that is that capacitance is epsilon A by D. In this case, we have mentioned it as epsilon naught A divided by x, where x is the distance. We remember from high school physics class that is actually epsilon A by D, where epsilon is epsilon naught epsilon r, where epsilon naught is the dielectric constant of free space. Epsilon r is a relative dielectric constant of the particular material that you are using. So this is the principle. In these cases, when you have a parallel plate capacitor, if you have one plate that is not moving or that is made of a, say, a rigid body, a metal, for example, another plate that is not a rigid body, that is going to change depending on the displacement, whose dimension or whose shape or geometry is going to change depending on the pressure that is applied, depending on the sound waves that it is detecting, depending on various phenomena, physical phenomena that are being applied, that are happening around it. In such cases, what will happen is the capacitance will change because the distance that the diaphragm moves, this diaphragm is made of a relatively flexible material, thus changing the dielectric, the distance, in this case epsilon naught epsilon r A by x, in this case x will change. If this x changes, then obviously the capacitance will change. Now, I can also change the area A. In this case, there are only three things that I can change. I can either change x, or I can change the area A, or I can change the dielectric constant, a different dielectric, displace the dielectric by a different dielectric. These are the only three things that I can change. But let's consider the case where I'm changing the displacement, the distance. In such case, this will also cause a change in the capacitance. Now, let's say that I'm able to measure the change in the capacitance. How will you measure the change in the capacitance? By measuring the output voltage across the capacitor, for example. I know what the capacitance is. If I know the earlier capacitance before this change, then I know the change in the capacitance as a function of the change in the displacement. Oh, using this, I can actually compute what the sensitivity factor of this capacitive sensor is. I can substitute for this, and I can say that the capacitance is, that the sensitivity factor is this epsilon naught epsilon r A divided by x squared. Now, let us look at the application of this in measuring displacement. Let us say how we can use the capacitive sensor to measure displacement. In this case, the amount of dielectric material that is there between the two plates of the parallel plate capacitor changes as a function of the applied displacement. Now, the total capacitance is a function of the areas and the distances. And since I know the areas A1 and A2, the capacitance is a function of the dielectric constants. One dielectric constant I know, that is the dielectric constant of free space epsilon naught, which is a constant, which is a universal constant. But the displacement I can measure, or the capacitance change I can measure as a function of the two relative dielectric constants, epsilon 1 and epsilon 2. The difference between these I can measure. And then I can compute the change in the capacitance. In this case, one plate is a fixed rigid body, metal disc, the other is a flexible diaphragm. Remember, how flexible this diaphragm is will define how sensitive this measurement system will be. No? If it is very rigid, then it is not going to respond to small changes. Or if it is too flexible, then it is going to respond to every little change. So the choice of which material to use depends on the particular application. Now that is where you come in as the biomedical engineer. You need to know what the application is. What is the range of values of displacement that you are interested in measuring? And appropriately design the diaphragm such that your diaphragm and your capacitive sensor will have maximum linearity and maximum sensitivity in the range of measurement that you are interested in. There's no point in designing a system that is going to measure everywhere, because that is going to be an expensive device. So always look at these problems from a design perspective. How will you do this? How will you design this? That design depends on what your application is. It depends on what is the range of values of displacement that you are interested in, and that depends on where you are going to place the sensor, what are the general ranges of displacement that happens in that particular part of the body, and so on and so forth. That is how you can maximize sensitivity and minimize noise and make the system affordable. You cannot have, we can have, technically, I was about to say that you cannot have a system that is both sensitive and also measures over a large range. You can have such a system, except that in most cases, this is going to end up as being very expensive. To make the system sensitive and noise free and affordable, you need to design it properly. That is where you all come in as biomedical engineers. That is the particular expertise that you bring. Any electrical engineer can design a capacitive sensor, but only a biomedical engineer will know what are the ranges of displacement that happens in particular physiological parameters. That is something that you bring as an expert in the field of biomedical engineering. This is a unique core biomedical engineering concept that only you can fill in, that non-biomedical engineers do not know. Why is it? Because they don't do courses on physiology, because they don't study about human body and parameters of human body. You study, and so you must know, and your design should be informed by this. Anyhow, let's continue our discussion. So the diaphragm in the sensing element is bent and designed in such a way that when pressure is applied, it has a deflection, and this deflection for a original radius of r is given by this formula. How did I arrive at this formula? Well, this is just basic mathematics geometry. Please do check this. I mean, so many such things I am asking you to check, not because I cannot explain, but because these are not principles of instrumentation. What I discussed just before in terms of design is biomedical instrumentation and medical device design. Now that is the core topic of interest for us in this course. This equation is actually from physics and mathematics, which you must be able to solve for yourself. So many such things I'm asking you to check. Now, please do check. Please do check. So that deflection y is given by this equation. So when the diaphragm is deformed, the change in the capacitance from the original capacitance is given by this equation at the bottom of this slide. So now I can measure the change in the capacitance. Let's take an application That application is, how do we measure sound? That is, what are the cases in which you are interested in measuring sound? When a person is speaking, you can use a microphone. For example, there are these capacitive microphones. But then, what is the biomedical application? A biomedical application is not just measuring a person's voice. Now, even as I am speaking, there is a microphone in my computer that is measuring my voice. But then here we are discussing about patients who are likely hospitalized and whose sounds that we are interested in. Now, what is the sound that is of interest for us? What is the physiological sound that has a critical consequence for us? Now, as a biomedical student, you must be able to answer that question. That is the heart sound. This technique, this method of using heart sounds to, or sounds in the lung, this method of using heart sounds to come up with or diagnose heart condition is also called as phonocardiography. Please do check what it is. Using a microphone, you measure heart sounds. A simple application is a stethoscope. Another example, another exercise that you can do optionally, this is slightly expensive to do, is to get a stethoscope, or you can get an old used stethoscope. Some of you can join hands together and contribute and get a stethoscope, open it up, and see what's inside. What is the principle? How is it working? There are actually digital stethoscopes available that not only you know provide the sound, they also have high dynamic range within the. I mean, they have high sensitivity within the dynamic range, but they also send the heart sounds by Bluetooth to the doctor's phone, for example. And this would be extremely useful during situations like COVID, when the doctor has to be away from the patient, but still the doctor has to listen to the patient's heart sound. A wireless device. The patient keeps the stethoscope on his or her own chest, and the doctor listens to the heart sounds in her own phone, for example. That would be a fantastic application of device. Now, how would you design such a device? Think about that. Anyhow, coming back to the topic, variation, we are interested in change in the capacitance. In this case, a capacitance microphone. What would be the output voltage of this capacitor? That would be this. That would be a function of the applied voltage and the displacement and the time constant. In this case, the time constant tau is RC. R is the resistance that is there. It does not change. Whereas C changes as a function of the relative dielectric constant. Relative or epsilon R. If you have a situation in which omega tau, in this case, is very large, much greater than 1, then you will see that in the range of interest, the change in voltage is essentially a function of the applied voltage by the deflection. This is approximation, and this is mostly true in the application of interest for us. Now, this RC circuit functions as a high pass filter. How am I saying this? That this RC circuit functions as a high pass filter? That you need to check from your electric circuit theory and physics. How does this RC circuit function as a high pass filter? That means that they are not really suitable for measuring low frequency signals. Now, that cutoff frequency at which this is going to be highly sensitive is defined by the specific characteristics and applications of interest. But please do find out why is this RC circuit considered a high pass filter, and how I can design an RC circuit as a low pass filter. Another exercise for you from your circuit theory. If you do not know that much circuit theory to understand why this is an RC, why this RC circuit is a high pass filter, and what is a RC circuit that acts as a low pass filter, do check standard electric circuit theory textbooks like Administer, for example. What are some of the applications of this capacitive sensors? Now, I already mentioned one of the applications, that is the phonocardiography. Another application is ballistocardiography and measuring respiration movement. I'm interested in measuring respiration rate in a bedridden patient. Now, measuring respiration in a patient who is moving in an outpatient is much easier. But measuring respiratory rate in a patient who is bedridden, continuous respiration rate monitoring requires having a capacitive sensor below the bed using dielectric layers that are placed below the mattress, so that you know as the person is breathing in, the dielectric change will be, the thickness of the dielectric will change. As the person is breathing out, more air will go, and there will be less load on the person. By the way, that means your dielectric layer uh, sensitivity must be so high to detect these movements, and it's absolutely critical to have this as a non-invasive devices. Why is that? Because an ICU patient is likely to have many such sensors placed on their body, that you cannot place one more sensor that is going to measure respiratory rate, but we are interested in measuring respiratory rate. So that is where design comes in. Design consideration should include all such considerations. So these capacitive sensors that are placed below the bed are relatively comfortable and absolutely non-intrusive, not just non-invasive, but they are also non-intrusive. And they are, another thing is that they are useful for measuring respiratory rate of neonates, babies. Sometimes this happens in babies, what are called as sudden infant death syndrome. For no particular reason, the baby will stop breathing. This is called as SIDS. This happens. This is not a very well understood pathology. There are some theories as to why this happens and how this happens, but an absolute clarity. By the way, we don't have absolute clarity on most things. That is different. In this case, a good scientific explanation of why SIDS happens is still elusive for us. But using such devices, using such systems, we can have a control system that alerts a nurse, for example, that this baby in this particular incubator is not breathing. If you have ever been to a NICU, you know how babies, there'll be a whole bunch of babies, all of them placed inside a neonatal intensive care unit. One of them is stopping breathing. Let's say an alarm is sounded in a room outside the ICU saying that this baby in this particular incubator is not breathing. It's important for it's critical for the medical care professional to know, so that immediately they can address this now. Because in such cases, if there is or if the respiratory rate is going down, so that before it stops breathing, before the baby stops breathing, you can actually take action. And that time that you have, response time that you're looking at, is in the matter of minutes, not hours, minutes, to save the baby. And every parent wants their baby to survive and survive for a long time, isn't it? So absolutely critical application is to use this in the neonatal cases and to study sleep, for example. It turns out that how people breathing patterns before, during, and after sleep varies, and there are signature patterns of breathing during sleep. Now it's useful to measure sleep patterns using breathing And it's a non-invasive method to measure this. Another application, again, a critical application, is to use capacitive sensors to measure pressure distribution inside the shoe of a person. This has critical application in diabetes, for example. Diabetic foot is a huge problem that is still not well addressed in a country like India, which happens to be the diabetes capital of the world. Here is an open problem that I invite all of you to consider solving. You can start a company to solve this problem. Diabetic foot. How to prevent foot ulcers in people with diabetes. How to ensure that people do not get foot ulcers, because once you get foot ulcers and once an infection becomes once sepsis sets in many cases it might be required, not in all cases hopefully, but in many cases it might be required to amputate the person's feet or legs. Now, how prevention is always better than cure. Now, what is it that you can do as a biomedical engineer to prevent sepsis or to prevent this infection from setting in by using your knowledge of such devices is something that for you to consider. You can start a company, you can have a startup. Remember, it's not just about selling things, it's about providing deep technological whole end-to-end solution that prevents this kind of problem. This is an open problem. I'm not saying it's an easy problem to solve. It's a very tough problem to solve. That's why multinational companies are not solving it. That doesn't mean that it cannot be solved. Just because somebody else is not able to solve a problem doesn't mean that we cannot do it. No, we should attempt. As biomedical engineers, I encourage you, I invite you to invest your time and energy in solving such problems. When you solve for India, you have solved for the world. What is it that you are going to do? Attempt to solve a problem in Indian healthcare. Now, you can use, for example, in such a pressure sensing insole, mica and corrugated metal layer based, capacitive sensors. Not just a diabetic footwear. This can also be used in sports, for example. Applied pressure essentially is a function of whether the person's foot is on the ground or in the air, for example. You can use this to study gait, for example. There are many different differences. So, capacitance changes. So, these are used to assess distribution of plantar pressure. These are also used to measure, similar sensors are also used to measure, the comfort of, of a seat. You're sitting, you're sitting and working, say, in a computer, in a sudden, or you're sitting and working, doing something. What is the pressure distribution of the seat? That also will define and determine your posture, and that could also have critical health consequences. Now, that is another phase. While you are sleeping, you can measure. While you are sitting, you can measure, and your foot you can measure. So all of these are specific applications of a simple technology. We'll continue the inductive sensor discussion in the next class. But what are some other applications? What are some advanced applications? For example, one other idea is to use MEMS based pressure sensor. This is an up and coming topic. Now, these are the topics that I want you to consider working on. Now, if you have a MEMS based pressure sensor, then you can use it to measure pressure in intravascular applications. I can measure pressure using this, because this way, if it is MEMS based, that means that it will be really, really small. And so I can measure this fundamental sensing principle can be used to measure pressure intravascularly inside. Another is, of course, we already discussed this, a non-contact, displacement and vital sign monitoring, whether the person is alive or not, whether the person is breathing or not. If you place the sensor below the bed, then you know whether the person is breathing or if the breathing rate is going down. Now, you can have a closed loop system that monitors the breathing rate and then informs the healthcare provider saying that before the person stops breathing, saying that the person's breathing rate is going down. You must address that, so that the nurse or the duty doctor will come and immediately address that. So that means Always look at how you can use the sensing principle in developing a closed loop solution. Look at a control system. Look at a whole solution. Don't just design a sensor. Look at a end-to-end solution that solves a healthcare problem. Okay. Polysomnography, sleep studies, and breathing studies. In many cases, spirometry, for example, spirometry is a method that we use to study breathing, is it not? In many cases, there is a nearly 100% correlation with in study of spirometry with study of breathing using non-contact methods using capacitive sensors. No, high correlation. In such cases, non-contact measurement is better than spirometry because not in all cases the person can, a patient can actually breathe through a spirometer, because maybe they are having other things going through their nose, other tubes going through their nose and mouth, for example, in an ICU setting, for example. Other advancements in this field include, for example, using advanced materials, advanced dielectrics. For example, gel-based dielectric or ionic gel dielectrics that have excellent response times. They respond really fast with millisecond response time. These are excellent approaches. Another approach is to use biomimicry. That is to use, for example, microstructures of electrodes and materials such that the area can be maximized by using the same material in morphology that mimics biological systems. For example, flowers such as hibiscus. So these are called as hibiscus microstructures. And there are several such applications. In this case, you will have an increase in area and thus an increase in sensitivity without compromising on other dimensions. So there are many such opportunities in this field that I invite you and I request you to explore. So with this, we come to the end of this discussion on capacitive sensors. We will continue our discussion on types of sensors in the next few videos. Thank you very much for your attention.